Boa tarde a todos. Sejam bem-vindos ao nosso terceiro dia do primeiro simpósio sobre plásticos reciclados no asfalto. É um prazer a gente estar aqui novamente. Hoje é o dia que a gente vai ter 5 apresentações de palestrantes internacionais que já tiveram experiência com o uso de plásticos reciclados em asfalto. Eu tenho o prazer de apresentar a primeira palestrante, a doutora Poulikakos. Ela tem graduação em Engenharia e Arquitetura pela Universidade do Colorado, em Boulder, mestrado em Engenharia Civil pela Universidade de Illinois, ambas nos Estados Unidos, e doutorado em Engenharia Civil pela ETH, na Suíça. Ela é atualmente cientista sênior no EMPA, que é o Laboratório Federal Suíço para Ciência e Tecnologia de Materiais. O foco das pesquisas está primordialmente em métodos de caracterização multiscala para o estudo químico e mecânico de materiais asfálticos. A doutora Poulikakos coordena o Comitê Técnico 279 do RILEM sobre resíduos e materiais secundários para pavimentação rodoviária. Dentro desse grupo, a gente tem um grupo de trabalho especificamente sobre o uso de plásticos reciclados. Ela já publicou mais de 80 artigos científicos e é editora da revista Construction and Building Materials. Lily, it's an honor for us to have you here. Thank you very much for your time, for sharing your experience with us. Now it's your turn. You can share your screen. Thank you very much.
Thank you very much, Camilla, and I'd like to thank you and also the SPRA organization committee for giving me the opportunity to talk to you about our experiences. So I will start sharing my presentation now, and you tell me if everything is okay.
We see your presentation. Just have to put on the presentation mode.
Yes.
Perfect. We can see it.
You can see it? Okay, great, great. So, well, hello, everyone. Hello, ladies and gentlemen. It's about 6 o'clock in the evening here in Switzerland, and I'm very happy to be able to share some of my experiences with you. And I'll be very happy also to answer your questions at the end of my presentation. My presentation is about 30 minutes. And I will talk to you, first of all, about an international cooperative opportunity, the RILEM organization, where we are addressing PE waste also. And I will then talk to you about our experience in a national project here in Switzerland. So today, the title of my talk is the use of PE waste in asphalt concrete, opportunities and challenges. We heard already one of my colleagues in the first day of the symposium already, I think, gave us enough motivation to work on this topic. He mentioned that there is 300 million tons of plastics worldwide, and 1/3 of this is polyethylene. So this is certainly a waste material that we should look at least and see if we can use it in our field. So the RILEM organization, that is an international organization where professionals are involved in who are active in construction material research, are coming together. They have various types of technical committees, and the technical committee that I am chairing together with my colleague Professor Pasquini from University of Padua is called Valorization of Waste and Secondary Materials for Roads. So we are looking at various types of materials. Our main goal here is to identify waste and marginal materials that are suitable as performance enhancing components for roads. We are looking at also possible polluting consequences. Anytime that we use waste as a product, we really need to show that it is not polluting the environment. And also life cycle assessment is a major part of our the work of our TC that looks at these materials as a viable option throughout their life cycle. Our goal is to produce recommendations for appropriate characterization methods. This is a very important part of our contribution because we don't know if our current characterization techniques are really giving us the needed results. And we want to make recommendations on suitable waste materials. Also the limit amounts, how much of it is practical and usable. So to answer these questions, we have formed 5 technical groups. As you see here, they are led by various experts from around the world. We have in our technical committee about 50 participants. Some are active, some are passive, but it is really a nice opportunity to have a discussion about all the topics. For example, here you see the various technical groups that deal with waste plastics, chrome rubber, waste aggregates, environmental risks, and life cycle assessment. The first technical group, TG1, that is led by my colleague Marian Tusar from ZAG in Ljubljana, Slovenia, has now 16 researchers. Also, Professor Vasconcelos from Sao Paulo is a very active member of this group. The topics that we are looking at in this technical group is, first of all, type of plastics. So right now we're looking at 2 types of polyethylene. We're looking at the preparation of these plastics for use in asphalt blends, the blending methodology, for example, high shear or not, the binder testing methodologies. There are questions that are coming up. Are, for example, ring and ball appropriate for our materials? Now, we have done a lot of the binder testing and binder blend testing. We are moving on to the mixture preparations. Should we use the dry method or the wet method? What are the mixture characterization techniques that are appropriate? So it is really through an international consensus that we can address these very important topics. And as I mentioned, our goal is to create recommendations that will be published starting in 2021. Now I will move on to give you some specific information about a national project that also deals with a similar topic. It's called Urban Mining for Low Noise Urban Roads and Optimized Design of Street Canyons. It's a long name, I know, but our general goal here is to look at two different challenges in the urban environment, that of noise and that of waste, and try to find solutions for these challenges, perhaps combine these. And our project is in cooperation with ETH Zurich, the technical university here in Zurich, and is completely supported by the Swiss National Science Foundation. We have a multidisciplinary team of experts. We have the team that are asphalt experts. We have the team that are acoustic experts, and two professors from ETH Zurich, from the environmental sciences and from architecture, are collaborators in the project. That because we have also two PhD students, and these are academic advisors of these two PhD students. The work that I will be, most of the work that I'll be presenting today is done by my colleague Rafi Kakar and my colleague Peter Michalenko. So our project has three aspects. There's the materials aspect, there's the noise, and there's the life cycle assessment. So of course, there's also synergies between these different aspects of the project. We are using a multi-scale evaluation approach. Most of the traditional tests in our field are what I'm calling here macro scale. In other words, our samples are a few centimeters big, and we are testing these samples and making conclusions about their in situ performance. However, we also in this project look at the microstructure. We look at, on the other end of the scale, I'm calling it here mega scale, we look at meter scale performance using a traffic simulator. Now, this is the largest scale that we have the capability of to characterize meter scale performance of slabs. And at the same time, we will look at chemical response, for example, PAH, polyaromatic hydrocarbons, for the various mixtures that we look at, and also leaching tests. We look at also noise properties of our mixtures, and of course life cycle assessment to see if these mixtures really make sense if one looks at the whole life cycle. Now, as far as which materials, then we've looked at the waste materials available in Switzerland. As you see on the top left of this slide, most of the waste materials in Switzerland are construction demolition waste. That is shown in yellow in this pie chart here. From construction demolition waste, part of it is recycled concrete. They could be a substitute for aggregates for our material. There's also municipal solid waste, and plastic waste is part of the municipal solid waste. And these can be used as either additives or also as aggregates, depending on their melting point. I will talk about that in a few minutes. So the criteria that we have used to choose our materials is, first of all, quantity. So there has to be a lot of it, and if these could improve the quality of our asphalt concrete samples. So I will move on now to talk to you about the binder characteristics that we've done so far. Our project has received some media attention. There's a link here where you can see some of our characterization techniques, as well as the first plastic asphalt road that was built in Zermatt in the mountains here in Switzerland. But of course, this is going to be in German. So you see on the top right, our team visited the recycling center, a plastic recycling center that is close to where we work in Switzerland. This is one of the biggest in Switzerland. And what they do is they take the polyethylene from wrapping, and that you see on the left-hand side, and they produce pellets out of these. And these pellets are sold further, and other companies buy them and they make different products, for example, pipes out of these. However, what our colleagues at this company, Recycling, told us was that in the process of producing these pellets, they produce also a lot of waste. And the waste you see piled up at the bottom of this slide. And these have to go to the cement industry to be used as fuel. So they can't do anything else with it. That's why we have now the pellets that are a bit purer and they can be reused. And we have the shreds that are basically the waste from the waste. And our main goal is to find uses for the PE shreds. So here we have also, in addition to PE shreds and PE pellets, we have looked at the PET coming from plastic bottles, also supplied by a Swiss waste management company here in Switzerland. And what we found out very soon is that these, the way we receive them from the plants are not, we cannot blend them into our binder. So we needed to shred them further, and the last row shows these materials after they were shredded. Now, it's important also, if we want to blend these plastics in our bitumen, in our hot bitumen, if they can melt. Now, we see that the melting point of the polyethylene, the two types of polyethylene, is below the mixing temperature in our asphalt mixture, which is 160 in our case, whereas in the PET it is not. So what we can use the PET for is a sand substitute, and that we have already done in a parallel project, or a parallel part of the project. And but in this case, we are using polyethylene as an additive to the binder, and we expect it to be melting within our binder. So we use a high shear mixer to add these to our binder, and on the bottom right, you see the various samples that were produced for further testing. So it is also important to know what is the characteristic of our material and the blends. How do they react when it comes to temperature? So here is the results of the thermogravimetric analysis. On the vertical axis, you see the percent mass. And on the horizontal axis, you see the temperature. And you see that as the temperature increases, there is a degradation of the material. There's a mass loss. However, our working temperatures around 160, where I put this vertical red line, we see that the mass is not changing. So our material is very stable within the working temperatures of asphalt concrete. However, as we increase the temperature, for example, as we start reaching 400 degrees, you see that the plastics by themselves, shown in pink and black, are a bit more stable. They are stable at a longer temperature, and the blends, the base binder shown in green and the blends in red and blue, they start to degrade sooner at a lower temperature until we reach about 500 degrees. There, with the performance of the blends and the plastics by themselves diverge, and we see that basically the blends are affected, the performance of the blends are affected by how much plastic is in there. You see that the blue and the red are show a different performance than the green. However, what is important for us to know is that at the relevant temperature, our material is stable. Now, moving on to further characteristics, using Fourier transform infrared spectroscopy, we see the chemical absorption, the absorption of the material at different wave numbers, showing if there are additional chemical bonds. So we have the plastics by themselves, again in pink and black, that follow the same absorption pattern. However, we see the black, which was the shreds, has some additional peaks. So these peaks are an indication that this is not as pure as the pellets, so it has some additional absorption peaks. However, when we look at the blends, the binder by itself in green and the blends that are shown in red and blue, they are completely superimposed. So the addition of our plastic did not change the absorption in our blends, meaning that we are not changing our material chemically. It is a physical blend. Now, I think that the dynamic shear rheometer and the results we get from this device are a very powerful tool in our field. Here we can see the modulus of these materials in function of frequency. And we have tested the material at various temperatures and frequencies and then produced these master curves. First of all, you see in black, we have the base binder 7100 with no thermal history. Then we have the blue that is the same 7100 that went through the same preparation procedure as the other material. So it went through some thermal aging. You see the modulus has increased. Then we have the polymer modified binder in green, and the two red and orange curves are for the plastic blends. Well, first of all, in the high frequency, low temperature regime that's on the right-hand side of the curve, we don't see a significant difference. However, on the low frequency, high temperature end of the curves, we see a significant difference between the plastic blends and the other materials. This could be an indication that we have a potential to improve the rotting resistance or the performance at high temperatures. Well, I want you to keep this in mind as I show you the results of the mixture tests in a few minutes. Also, from the DSR results, we can look at the black curves, what we call the black curve that shows the complex modulus versus phase angle. So this is just the raw data. There was no shifting or fitting or anything like that. So it gives us the behavior of the material. And again, you see I've drawn a red line, and if you look at what's happening above the red line where the modulus is higher, we see that these materials behave similarly. However, once we go to the lower modulus values where the material is warm and the modulus is lower, then we see a big difference between the different materials. So green shows the base binder, and yellow is the polymer modified binder, red and blue are the PE modified binder. So here we see a definite divergence from the base binder, and we see the effect of plastics a lot clearer. And for example, if we look at the same value of modulus, we see a much lower phase angle in the plastic modified binders than the base binders, meaning that the material is more elastic. So the plastics are contributing to the elastic part of the complex modulus, whereas the base binder is more viscous. Now I'm going to show you some microstructures that were done using electron microscopy on top left of the screen. You see that when the binder is exposed to the electron beam, it forms a microstructure. And on the left-hand side, we have the base bitumen. On the right-hand side, we have the base bitumen with plastics. So we see that the plastics did not disappear. They are present in our binder, even though it's above their melting temperature. Now, we have done some experiments using the stability test, and we looked at the viscosity of the top part of the tube and the bottom part of the tube after this tube was exposed to high temperatures for a certain amount of time according to the standards. And we see, as shown in the bottom diagram, that the top viscosity is much higher than the bottom viscosity. So that shows us that most of the plastics, after the bitumen becomes hot, are moving to the top. And therefore, there's a segregation and a stability problem. And this is very important to keep in mind when it comes to storing this material, for example, in a bitumen tank for an extended amount of time. So what did we learn from the binder investigations of these two types of PE waste materials? We have seen that there is certainly a divergence in behavior at higher temperatures from the base bitumen and from polymer modified bitumen. The higher modulus values could be a reason that we could use this material for improved rotting performance. And we also saw that there's a storage stability problem and a segregation problem. We also would like to emphasize that the low temperature behavior needs to be studied further. Now, I will move on to talk to you about the mixture performance. I will also show you the results of the experiments we've done on the noise reduction properties of these mixtures. So, as I mentioned earlier, our focus in our national project is on semi-dense asphalt. This is a special type of asphalt that is considered low noise and is widely used in Switzerland. This diagram shows you the various types of mixtures that are available in Switzerland, for example, and also their the contents of these different mixtures. So on the right-hand side of this diagram, you see PA, or porous asphalt. That is a material with the highest porosity that is being used, but also our SDA is very close to that. It's not as porous as the porous asphalt. And you see also, for example, asphalt concrete in the middle of this diagram that has a bit more sand and filler compared to the PA and the SDA. So the mixtures that we have used have 16% porosity or air void. They have a binder content of 6.1 or 6.5%. And the ones that are modified with polyethylene have 0.3% by mass of polyethylene. There are various ways of producing the mixtures, and there is the dry process where the additive or the plastics can be added to the hot aggregates, and then the hot bitumen filler is added to it. Then there is the wet process where the plastics are added to the bitumen, and then there is a storage period where they interact with each other, and then this mixture is added to the hot aggregates. This method also is used for chrome rubber modified mixtures. And there is the semi-wet process. We are not using the wet process in our project. What I'm going to show you now is the semi-wet process. We have also used the dry process, but the results that I'm showing you now are the semi-wet process, where we have defined it as we've added the plastics to the hot bitumen. However, there is no storage. They are added then immediately to the hot aggregates plus the filler. So we used the gyratory compactor to compact these mixtures, and what was striking was the ease of compaction. So adding just that small amount of polyethylene made a big difference in terms of compaction. So there were less number of gyrations that were needed and less compaction energy, as you see here for both polyethylene modified mixtures that we looked at. So we used a small mixer, as we had we could not produce a large amount of shredded PE waste to do our experiments. Now, once the mixtures were compacted, we cut these and impregnated and polished them, and so that we could be able to look at them with the electron microscope. Now, it is clear here, you see that you see the sand aggregates, and you see the mastic with the filler. However, what is very interesting is also one can recognize the pieces of plastic that were inside our mastic. This is very important to realize that the plastics do not disappear. They're still there, and maybe they partially melted, but they didn't completely melt. And when our mixture becomes hot, then and our binder becomes very viscous, then our plastics are still there and they add elasticity to the mixture. That's just to keep in mind. We have so far we have looked at the cracking performance and the high temperature performance of the mixtures. So the two ends. So if our material is like at low temperatures, it can be prone to cracking. At high temperatures, it can be prone to rotting. And so we have looked at behavior at these two ends. We have other experiments that are also planned. So far, the results at the low temperature end, comparing the polymer modified mixture with the two plastic mixtures, it shows the similar fracture toughness, I would say, at 0 degrees for both of the plastic modified mixtures. And if we look at the fracture energy, even the plastic modified mixture that had more binder was performed a bit better. So I can say that in general, we could reach the low temperature cracking performance of the polymer modified mixture. And if we look at the high temperature performance, we've used the cyclic compression test, where it registers the strain in comparison to the number of cycles. And if you see on the blue curve, after a while, the deformation becomes so large that the increase becomes exponential. So we like to basically move this turning point towards the right-hand side of this diagram. Now, these are the results that we have. First of all, in green, it was the mixture that we used the straight run bitumen for, and the red and the black are the ones that had PE in them. So we were able to move the turning point a bit to the right, however, not enough to reach the polymer modified mixtures. So I think that so far, then our results are, even though in the binder test we expected that the high temperature behavior would be comparable to PMB, we could not reach that when we saw the mixtures. And a mixture's performance. So the low temperature we came close, the high temperatures we did not. So the mixture needs to be more refined and adjusted. Now I will move on to give you some information about the noise reduction properties, because once we change these mixtures, we want to make sure that they still can be used as a low noise pavement. And one of the important parameters for low noise pavements is surface texture, and we're using a laser scanner to look at this property. As you see here, you can get very interesting results once you use the laser scanner. And so we looked at the texture of these materials, and according to the international standard, the region between 0.5 and 5 millimeter wavelengths correlates with noise reduction. So you see that the tie road noise correlates with the macro texture. And so in our project, we're looking at various types of mixtures, not only PE mixture, but here you can see a whole range of them. And the PE mixture is shown in red, the control polymer modified is shown in black, and you see that in the region that is important for noise, we don't see a significant difference between the reference and the PE modified mixture. So as far as surface texture is concerned, we are not at a disadvantage. Then another parameter that we're looking at using noise absorption properties at various frequencies, that is done with a tube test that is shown on the top. Again, this is a result for various mixtures that are used in our project, and the PE modified mixture here shown in cyan does not divert too much from the black one at the relevant frequency range. So also we can say that there is no significant change in the noise absorption property. So we did not lose any noise absorption property by using PE as a waste material in our mixture. Now we have also various things that are ongoing. For example, the very important area of environmental assessment. We are performing leaching tests. Here there's an image from a mixture that had crumb rubber in it, and so we're looking at what leaches out in the water. And in this case, we would like to also look at microplastics. That's a big topic right now, and also the idea of if our bitumen can keep the microplastics intact and that not allowing it to leach into the water, that would definitely be an added advantage. So we're cooperating with our colleagues, both at the European, at the international scale through RILAM, and with our colleagues at EMPA to look at this topic. And as I mentioned already, there's a PhD working on the life cycle assessment. The method that he's using is from cradle to grave, so the whole life cycle. And one of the topics that is very important that he's looking at is if there's a burden shift. For example, I mentioned to you that the wastes that we are using are used by the cement industry as fuel. Now, if this is not used as fuel, then the cement industry has to look for other kinds of fuel. So he is looking at the whole story, which is very important. Also, the large-scale experiments using a traffic simulator is going to, I'm hoping we can do those now in 2021. We've already planned those, and those will give us some indication of the large-scale performance of the materials. I hope that I could give you an overview of the challenges that this use of plastics and asphalt pose for us. For example, the appropriate characterization methods. I'm hoping that our cooperation in RILAM can shed some light into this through the discussions with our colleagues. Also, the mix design, how much of these materials, what kind of binder, all those are very important challenges that we have to address. Also, I spoke of the environmental assessment. I consider that also as a important challenge, the leaching and microplastics, how to do this. And this has a lot to do also with the acceptance of using waste in asphalt concrete and basically overcoming the barriers that exist for the acceptance of these materials. Of course, the benefits, I think, is clear to everyone. We heard from other speakers that plastics are a huge problem worldwide. Perhaps we can use these in our materials as performance enhancing material. We can reduce virgin materials. For example, instead of using virgin polymers, we could use the waste plastics. If it works, then that would be a definite benefit. We are hoping then to optimize the mixtures in the future. Binder content and binder type are very important. Also, other mixture testing methods, looking at rotting and complex modulus and raveling. The special mixtures that we're using, the SDA, have a raveling problem, so it's important to have the right experimental methods to mimic the raveling they experience in the field. Of course, the life cycle assessment I mentioned several times, and the whole idea of a burden shift. So that brings me to the end of my presentation, and I thank you for your attention, and I look forward to answering any of your comments.
Thank you very much, Lily. Very nice presentation. A lot of information from the studies conducted at EMPA. Thank you very much for sharing this with us. We have a couple of questions here. The first one is from Professor Adalberto Facchina. He said, nice presentation. Do you have test sections using asphalt mixtures produced with recycled plastics in Europe?
So the first test section in Switzerland was produced in Zermatt. And this was not done by us. It's done by one of our colleagues. And actually, it's only 1 year old. And I just received some cores from this section. It seems like it's performing well. And so it's not a heavily trafficked road. It's in a village in Switzerland, but it is in a cold region. So it does experience a lot of temperature variations, and it's basically 1 year old in Switzerland. As far as in Europe in general, there are plastic roads, I believe, in the UK, because there is a company that is producing these plastic waste and plastic waste for asphalt. And I believe that they, in Scotland and in the UK in general, they have produced some sections, but I don't have any information about this.
Thank you very much. The next question is from Rafael Martins from Creighton Polymers. Great presentation. Did you evaluate the raveling performance of the different mixtures?
The raveling performance we have not tested yet. Actually, we don't have at EMPA a device to measure raveling. However, in a parallel project, I looked at chrome rubber modified mixtures, and we sent those to Germany for raveling tests, and we did not see heavy raveling. But in situ, I have from my colleagues who build these mixtures in situ, I know that there is a problem. However, in our lab right now, we do not have a method that we can use. There are some research projects going on, though.
Very nice. The other question is from Zila Mascarenhas, our graduate student. She said, thank you, very nice presentation. Regarding the Riley MTC, is there any investigation about the multi-recycling of asphalt mixtures with plastic waste? And the second question is, do you think it will be viable in the future?
So we are going to end this TC in 2022, and we're starting with our TG leaders to talk about a follow-up TC. And definitely recycling will be a topic that is addressed in the follow-up TC. Right now, we're looking at the materials themselves. Recycling is not part of it, but we are hoping that there will be a follow-up TC to address recycling.
Very nice. The next question is from Professor Tiago Aragão from Rio de Janeiro. Great presentation, Lily. I saw that you consider the multi-scale approach in your studies. I wonder if you could identify significant microstructural changes in the binder modified by plastics.
Yes, I did, and I showed it. Should I show it again? in one of the slides, I did show this. There's a microstructure of the plastics modified, the binder modified with plastics, and there was a microstructure of the mixture. Should I share this, or will you have this? It's on slide 22.
Okay, I guess since everything will be recorded, I guess everyone can go back to the recording after the presentation. I think it's better.
Yes. So the binder with the plastic was imaged using an electron microscope, and we do see a difference in the binder without plastic and the binder with plastic. Even though it was added at above the melting temperature of the plastic, it still shows up in the microstructure. Also in the mixture microstructure, it did show up.
Good. Next question. It's a lot of questions for you, Lily. From João Pioli. Also, think in terms of general application of recycled plastics to build roads. What is, in your opinion, the most promising technique, the wet process or the dry process?
So I think that we don't have a choice but to use the dry process, because as we saw in the wet process, there is a storage stability problem. As our results show again on slide 22, when we do a stability test, the plastic basically is lighter and it moves up. And so you have a huge segregation problem. So it is, if we use the dry process, we add it directly to the aggregates, and then we add the bitumen, so we don't have we have less of the segregation problem.
Very good. Our last question here is from Leni Leite, also from University of Rio de Janeiro. She said, congratulations, very good presentation. Is there enough polyethylene pellet to use in asphalt in Switzerland? Is it a project that can be used in the field immediately?
So, I showed that there is two types of polyethylene. So the polyethylene shreds are right now, they are just burnt in the cement factory as fuel. So if we can use this as an additive to our asphalt, then that would be great. But again, we have to look at the life cycle assessment to see if it's worthwhile to use this. If we look at the totality of the performance within the life cycle, and whether or not there is enough. I think that we use very little of it. So even if a small percentage of the roads that are, for example, right now polymer modified, they would use polyethylene instead, then we could use up this material definitely. So there's 16,000 tons right now of pellets that are used, but these are used to make other products like pipes. But it is the shreds that are burnt, and we don't really know if it's better to burn them or is it better to use them in the road. So first we have to prove the performance, but there is a lot of it, and as also we heard from the first speaker, there is a lot of polyethylene. There's like 37% of the plastic market. So I think that the quantities are enough to cover our purposes.
Thank you very much, Lily. We do not have more questions from the audience. I thank you again for your time, your availability, and for sharing your experience. And we hope to have you soon in Brazil for what is coming next in Europe and in Switzerland about the recycled plastics. Thank you so much.
Thank you very much, Camila.
Bom, gente, a gente vai finalizar essa primeira apresentação. Vocês podem permanecer aqui, a gente vai só fazer a transição entre os palestrantes e voltamos aqui nessa mesma live, tá bom? Aguardem só um minutinho, agradeço a todos a presença.
Boa tarde, pessoal. Sejam bem-vindos, então, à nossa segunda rodada aí, nossa segunda palestra do primeiro simpósio sobre plásticos reciclados no asfalto. Nessa segunda palestra, vamos ter conosco Richard Willis, ok? Richard Willis, ele é vice-presidente de Engenharia, Pesquisa e Tecnologia da ANAPA. A ANAPA é a Associação Nacional de Pavimento Asfáltico. Richard Willis atua como especialista do ANAPA em projetos de mistura, materiais reciclados, análise de custo de vida e projetos de pavimentação. Ele serve aí como elemento também nos comitês de pesquisa e tecnologia de asfaltos do ANAPA, Conselho de Engenharia, Pesquisa e Sustentabilidade, Comitê de Desenvolvimento de Mão de Obra e o Task Force de Análise do Ciclo de Vida do Comitê de Economia do Pavimento. Além de ser também co-apresentador do podcast Paving Black da ANAPA. Antes de ingressar na ANAPA, Richard trabalhou como professor associado de pesquisa no National Center for Asphalt Technology, na Auburn University, e enquanto estava na NCAT, ele também conduziu diversas pesquisas sobre tópicos relacionados a materiais reciclados, sustentabilidade, caracterização de mistura, entre outros. Bem, o Richard também, ele é formado em Ciências Físicas pela Freed-Hardeman University, e tem mestrado e PhD pela Auburn University. So, Richard, thank you very much having you here with us. It's a pleasure. So, in honor, also having you here sharing your experience and knowledge with our Brazilian and also a very broad audience that having here. Okay. So,
thank you.
And the screen is yours.
Well, thank you all very much for this opportunity to come and share a little bit of what we've been doing at the National Asphalt Pavement Association on the subject of recycling plastics in our asphalt. There's, for those of you who aren't familiar with NAPA, we are the National Asphalt Pavement Association. So that means we're the trade association that represents the asphalt industry. Our primary members are the people who produce our asphalt mixtures, so the people running the plant. But we also have members who are just lay-down contractors, and we have associate members who might be material suppliers or equipment suppliers and manufacturers, consultants. And if we look at what the mission of NAPA really is, we have a three-pronged approach to how we work with the industry or for the industry. And the first thing we do is we try to support it. We try to ensure that our members have what they need to run their businesses to produce high-quality asphalt mixtures. We advocate for the industry, and whether that's before the United States Congress, it could be before regulatory agencies such as the Environmental Protection Agency or OSHA, which is our health and safety organization, or even Federal Highway Administration, but ensure that those organizations who write the standards and develop some of the rules understand the position of the industry and how these rules will impact it. And the third thing that we do is we advance the industry. And whether that's through technology or getting a better understanding of how things like recycled plastics might impact our industry, we want to continue to help make sure it's moving forward and that we are putting our industry in the best position possible to provide what our customers are looking for. So coming back out to the idea of this presentation today, I'm not going to be showing you massive amounts of data or charts. One of the things that we had to do early on was kind of take a landscape and figure out what do we know, what don't we know. And it was great to hear the presentation before mine. We saw that there were definitely some things that they were learning that we hadn't applied or hadn't heard. And I wish I'd been able to be a part of more of these sessions over the past few days. But what we're going to do is look at things from a 30,000-foot view and look at what's going on, what do we know about plastics and some of its basics, and then understand what do we know, what do we need to know, and really the path forward to ensure that as we look at these materials, we're making the right decisions and we're not moving things too quickly. So in the United States, the Federal Highway Administration, or FHWA, sets a lot of the policy with which the Departments of Transportation really focus on and follow. And in 2015, I think FHWA updated a really important policy, especially as we start looking at the use of recycled materials in our asphalt pavement. And while there are 5 specific bullet points in this policy, it really focuses on the 3 things, or the 3 E's. And these 3 E's are the engineering, the economic, or the environment. And the policy says that they encourage using recycled materials, but there needs to be some kind of engineering analysis to ensure that it makes sense from a longevity standpoint and we're not hurting the performance of our pavement. It needs to make economic sense. There are a lot of these materials that people are looking at putting in pavement that have to go and go through additional processing. And these additional processes are going to add cost to the mixes. And is that going to increase the cost that these DOTs are having to pay in order to adequately use them? So does it make economic sense? And then finally, does it make environmental sense? Yes, we're taking recycled materials and we may be moving them out of the landfill. But if it doesn't impact the performance of the pavement in a positive way, we may actually be doing more long-term environmental damage by having to go back and repave more often and pull more materials out of the ground. So understanding what those true impacts are, and similar to the presentation before mine, does it impact leaching or the components when that water runs over the road? So really looking at things holistically and understanding, is it beyond just a feel-good story, but is it the right thing to do? And is it the responsible thing to do to actually recycle these materials? Now, in the US, this really kind of came to a head when the national sword policy in China said, we're not going to be taking any more recycled plastics from other countries. Because if you look at the data that the EPA shows, up to about 2017, we were generating about 36 million metric tons of plastic waste in our country every year. And of that, we did recycle about 8 to 9% of it. Another 8 to 9 million tons was maybe used for the combustion of natural energy. But the majority of that material, around 26 million tons, went to landfill. And when we look at this material, now that we are not able to export plastic waste, this number is we're going to see trends in this going up significantly over the next few years. And that's when I say asphalt went viral, because you started to see numerous things happening. You started to see companies that started marketing very heavily the idea of using recycled plastics in asphalt. And in fact, one of the few times this I hope ever happens, my mom broke the news to me that people are starting to really look at putting plastic in the road when she sent me a Facebook post that she saw with this video of how our world is going to change because people were now putting recycled plastics in asphalt. But it was a very visual problem. It was something that people could see because when they went to the ocean, they saw the plastic waste, they saw the pictures of the plastic islands in the Pacific, they saw the pictures of the dolphins with the six-pack rings around their noses. We saw all these pictures, and then it went beyond social media. Traditional media, such as the Washington Post in the US, picked up articles and started writing about it. The Economist, of all places, wrote an article that basically said, asphalt's basically a polymer, plastic's basically a polymer, why can't we just switch them out? And I knew things were going to get really, we were going to have to look at this issue hard and fast, when in late November, I got a call from our government affairs VP, and he said, Richard, it just hit Congress. In the Addressing America's Surface Transportation Infrastructure Needs hearing, a congressman asked a contractor from Texas, so we just heard about all this plastic waste going on and what we're doing with it. What are y'all doing about recycling? It became more than just something that was social media buzz. It became something that became full front and center of our association and what we needed to be looking into. Around the same time, we started reaching out to organizations such as the American Chemistry Council, because the American Chemistry Council had set very lofty goals that by 2030, every piece of plastic film was going to be able to be recyclable. And by 2040, that every piece of plastic film was going to be able to have an end use. They were going to have a home for it. The Plastics Industry Association was reaching out to us because they understand plastics. We don't really understand plastics. We understand asphalt. They don't really understand asphalt and its chemistry and the work. And so we started working together to try to help them understand what questions really needed to be answered to figure out if this is a viable long-term material for the industry. I think we also need to step back a little bit. And again, it goes back to asking that question, is it good to recycle? Yeah, I mean, I remember growing up as a kid in the 80s and going to the garage and taking the Coke cans that were aluminum, smashing them with a sledgehammer, putting them in a bag and taking them off to get a few cents or a dollar or two for recycling. And I thought I was doing something great for the world. But the reality is that was a very limited view. It wasn't thinking about, well, what's going to happen now that this material is no longer my responsibility? What's it being used to do in the future? And so in the asphalt industry, there are different materials that we've used as recycled materials pretty regularly. The first is wrap. Now, if we think about wrap, in the US, we average around 22% wrap in every asphalt mixture today. However, it's taken us 40 years to really get to the point where that is where we are. It's taken research. It's taken time. It's taken us having failures. There were times where we pushed the wrap content too high. It impacted pavement performance. And then we've had to pull it back and learn. But that's the gradual process that it takes when we start introducing these new materials into our asphalt mixtures. Similar thing happened with recycled asphalt shingles. When the polymer spike happened in 2008 in the US and the prices of polymer and asphalt binder went through the roof, people turned very quickly to asphalt shingles because they said, well, it's asphalt, we can replace one with the other, bring down the prices of our mixes a little bit, be a little bit more sustainable because we're now not having to pull in new virgin materials, and we can make our mixtures work. And what happened is we pushed that too far, too fast before we really understood the long-term ramifications of using recycled shingles. And now we've had to pull back. And around 2014, 2015, as an industry, we were using shingles pretty regularly. But after that happened, and when people started getting worried about performance, we saw a drastic drop-off in the amount of shingles that people were putting into their asphalt mixtures. And we've started to now see a little bit of a plateau from that drop-off. Another area is recycled tire rubber. Recycled tire rubber was interesting because in the 1990s in the US, Congress basically told the asphalt industry and the DOTs, you're going to use this. We're going to mandate that you use recycled tire rubber in your asphalt mixtures. But at the time, the science wasn't ready. There were people that could use it effectively, but there were people who couldn't based upon the technology which was available, what we understood about how do we incorporate this into our mixtures, and how do we use it effectively. And what happened was there was a drastic kind of pushback. Congress repealed that mandate and said, nope, you don't have to do that anymore. But it took years and years and really a couple decades for people to start looking effectively at the use of recycled tire rubber in the US again. Now we get to the idea of plastic. And I think we need to take a look at what we've done in the past as an industry and learn from some of those challenges, some of those mistakes, to ensure that we are not doing anything to compromise the performance of our mixtures. It was briefly mentioned earlier about the different types of plastics which are available. And the challenge that we have in many times is this isn't just an engineering problem. It's a communication, it's a public relations challenge in many ways, because people will say, it's plastic. But in reality, there's so many different types of plastics. They have so much different chemical makeup. There are times when plastics are layered and put together. There are times where plastics are contaminated with food, and we have to understand what are those plastics and what are the impacts that they could potentially have on the way our mixtures perform. Because as was mentioned earlier, polyethylene is really where most of those people are looking at plastic waste. But there are other different types of materials as well that people might think, could I do this? Could I use this? Or with a politician, they'll just say plastic and not understand the level of complexity that we have. When you look at the US numbers, this is the breakdown from municipal solid waste. About 30% of our plastic waste is low-density polyethylene, linear low-density polyethylene, or high-density polyethylene. The majority of the other 70% are the PVCs, the polystyrene, the polypropylene, the others. And if we're really focusing on polyethylene, we're seeing that there's a really limited number of tonnage that we could actually use for that recycling process. The other thing that really needs to be evaluated and looked at is the plastics recycling process. There are 4 basic kind of steps that a lot of people use. There's collection, there's shredding, there's a washing, there's a decontamination process. And if we're really going to get to the point where we can put recycled plastics or recycled plastics in the way that people have set these goals, it is a significant, it is a multi-billion dollar investment that's needed to ensure that this is done properly. But that all kind of gets us to the point where we're trying to understand, what do we know? What don't we know? So as a good former PhD student, professor, when in doubt of what you know, do a lit review. And so the great thing about being on the other side of the desk now, necessarily not at the university, is I can pay for someone to do a lit review and not necessarily have to be the one doing all the literature myself. And so we hired the Asphalt Institute and NAPA formed a joint task force, and we hired the National Center for Asphalt Technology to look into this for us. And they did a lit review where they looked at everything that they could find that had really been published or they could document in some way. Again, this was limited to articles that we could find in English, but we looked at over 110 different articles from 1991 to 2020. We did have to kind of draw a line in the sand at some point and say, we're not going to take any new information just because we had to go through editing, we had to go through review, we had to go through that process. But we thought we had a pretty good compilation of what had been done to that certain point. When we look at this, 22 of these articles were from the United States. We had a few that were from India who had been using the dry process for a while, Malaysia, Canada, China, and then you had a lot of those countries where we'd just been able to find like an article on it, and we had 5 where we didn't know where the research was conducted. When we look at the type of plastic that was out there, and this again goes back to show that while polyethylene is the predominant type of material that people are looking at, really everyone's looking at everything. We have most of the different types of plastics where some kind of evaluation is being done on how it can be used effectively. But again, most everything is that polyethylene process. Most of the literature review most literature was done on the wet process. We did have about 35 articles that were looking at the dry process, but 57 were on the wet process. 10 were specifically looking at a product that had been used in the 1990s in the US called Novapulp. Polypulp was another. There was a little bit of an emulsion, and 6 that didn't specify what they did. And then the majority of the work did really focus on just that laboratory testing. There were some field projects, there was a little bit of lit review, but when you start thinking about things like the impact on cost, which is important, the impact on pavement design, which is important, there really has not been a lot that's been published. So as we look at this, again, kind of from that 30,000 foot level, let's go through a few of the things that we learned from this evaluation. And if we look at the first thing is the wet versus dry. when you look at this, the challenge that many people are dealing with is that there's different language out there. There's sometimes where people talk about this is a binder modification. Like I'm going to replace my polymer. I'm going to use it to stiffen the asphalt binder up and help its performance in terms of that way. There are other people that are saying it's a binder replacement, where they're saying, you know what, if you add 10% plastic to your binder, you can actually remove the amount of asphalt in your mix. That plastic is going to take the place of the binder. That is one claim that I have not seen much data to back up. I will say we have seen data that it does modify the binder, and we'll get into that in a second. But I think we need to be very, very careful when we're thinking about binder replacement. In the US, the primary distress that we see is cracking. And binder quality and quantity are two very important parameters that impact the cracking resistance of an asphalt mixture. And as we start talking about taking binder out of our mixes, are we going to then drive that cracking performance down and make our mixtures not perform? But in the wet process, what we saw is anywhere from 2 to 8% by weight of the binder, depending upon what they were doing and what material they were evaluating. The critical issue with the wet process is you need a low melting point in that binder. You need to make sure that it will be able to melt. It'll be able to quasi mix with that binder and blend so that you can ensure good dispersion throughout your material. On the dry process, we've seen it as an aggregate replacement, a mixture modifier, or an aggregate modifier. There are some places that say if you use the dry process, the plastic's going to melt around those aggregate particles. It's going to decrease the absorption of the aggregate. It's going to make that aggregate stronger. And we're actually doing some research right now with the National Center for Asphalt Technology to evaluate those claims and see if that is really the case and it's an aggregate modifier and not as much of a binder or a mixture modifier when you look at this. In these instances, people are putting about 0.2 to 1% by weight of the aggregate into the mixtures to help you understand the amount of plastic that we're using in most of these cases. When you look at binder performance, this is really important when you start looking at things like the wet process. And as was easily expected, and one of the things that we expected to see, plastic stiffens your asphalt binder. However, there's really been little data that has looked at things like fatigue or the low temperature performance. Most of the data or most of the studies looked at things like penetration, the softening point, the viscosity, the ductility, and some people started looking at performance grade. The overall consistent finding was that the use of recycled materials reduced the penetration and ductility, increased the softening point, viscosity, and the high temperature performance grade. Therefore, you're going to improve the rutting resistance of the mix. However, other studies, other than the reduced ductility, various studies looked at the fatigue or low temperature performance. As was shown in the previous presentation, phase separation tendencies are extreme with some of these plastic materials. However, there's potential to use stabilizers similar to what we use with our recycled tire rubber in the US to help with the separation tendency. I know the National Center for Asphalt Technology has worked with the Plastics Industry Association to find some of these materials and help with those problems. Some of the other challenges that we have are that polyethylene is insoluble in many of the solvents that we commonly use to extract and recover our binders. So when we do that, it's going to be hard to fully characterize these asphalt binders that we've had in the field when we put recycled plastics into them. On the mixture characterization side of things, a lot of this really looked at things in terms of Marshall stability. And in most cases, the addition of recycled plastic increased the Marshall stability and the Marshall stability index or quotient of these mixtures. Several researchers have suggested that this is going to be improved rutting resistance or improved resistance to permanent deformation. And existing studies also demonstrated a positive impact of added recycled plastics on the stiffness and rut resistance of the mixtures. And this wasn't that much of a surprise to us. But again, I think it's interesting to note, try to understand the mechanism. When you look at the increased rutting resistance, on the wet process, people are saying it's because of the stiffer binder. On the dry process, many are claiming it's because of the increased aggregate friction that is happening because of the plastic on the aggregate. Very few people have really looked at the moisture damage characterization. The few studies that have shown that there is either a positive impact or no impact, but it's something that additional research needs to be done on. And again, one of the big kind of gaps in all of this is we're still haven't done a lot of understanding on how it impacts cracking performance, especially when we long-term age these mixtures. As someone representing asphalt contractors, one of the really important things to me is how does it impact plant operation? Most of the documentation on plant operations only relates to NovaFold. And they had to bring the high shear blending unit onto site to ensure that this was mixed properly and it was done well. But that's really about all we know. There are some places that have said it's just like using anything else. But again, it's something that we need to have a better understanding of. And we'll get to that when we specifically look at some of the questions that really need to be answered. Construction is another topic that's very important to our industry. If we start using it, is it going to make it more difficult to compact? Is it going to be easier? There was one study that actually documented construction, and they suggested it was difficult to compact. They had to use heavier rollers to get the compaction that they wanted. In conversations and emails we've had with a French construction company, they have said that it is a very temperature sensitive material, but compaction is not an issue. This company has been using plastic modified asphalt for years in their high modulus mixes in France. So it's something that they do have experience with in a very specific and controlled environment. We also want to ensure that as we're putting these new additives and changing our mixes, we're looking after our workers. And so we look at things like health and safety, and there are two potential concerns in literature, and one of them was mentioned earlier, the leaching of toxic components. One study has suggested that there's no adverse effects, but again, it's something that we're going to need more data on and a better understanding, and it may be something that we have to look at by plastic type. The other main concern is when PVC is heated up, it emits chlorine-based gases, which can be very, very dangerous from a health and safety standpoint. So PVC should be off the table really for something that we don't put through our plant. We don't want to make sure that this is something that we stay away from and that we don't have as a part of the research studies that people are doing. On the environmental side of things, I was really happy to hear some of the LCA work that's being done on this. There are potential environmental benefits to using recycled plastic, the preservation of resources, the reduction of solid waste, and potential emissions reduction. But there are potential environmental concerns, such as microplastics. As the wearing surface, that asphalt that's on the top of the road gets worn down over time, do the microplastics then get put into the environment? When I'm milling this pavement to one day replace it, do microplastics get put up into the air and could potentially then expose workers to where they breathe at? The future recyclability of these mixes is really important to the industry. If you look at the numbers in terms of recyclability, we're talking in municipal solid waste, if we totally have 36 million tons of recycled plastics. Last year, the asphalt industry in the US recycled over 89 million tons of wrap and put it back into our mixes. So it's a gigantic number. And if we're replacing a small amount of plastics and making it where then we cannot recycle these mixtures so that they perform in the future, we're replacing a small problem, and now we have to figure out what do we do with all these asphalt mixtures when they get old. So there's a lot of ongoing work. I know that the Federal Highway Administration, the American Chemistry Council are looking at doing some of these life cycle assessments in the US to understand the environmental impact. And it's something very important for us to do. But ultimately, it's got to perform in the field. And when you look at the literature review, there are over 200 field projects which have been documented. And most show you improve the rutting, but you get more cracking. Additional field projects are happening. There's in India and China and Canada and New Zealand, the US, we've started doing a few recent field projects as well. And what we need to do is understand where everyone else is, what they're doing, and learn from each other as we get data from these different field experiments. The reality is there's still a lot of knowledge gaps out there before we can fully understand, is it responsible to recycle plastics and asphalt mixtures? One of those huge knowledge gaps is the sourcing of your plastic. How do I spec it? How do I write a spec so that I can have confidence that the plastics I'm putting into my mixtures are going to be safe, they're going to be economical, and they're going to help my mixes perform long-term in the field? We're actually going to start working with the Plastics Industry Association in the US to try to help develop some specs and some standards which we can use to understand this. Because when you look at some of the plastics which are being supplied to people, there are some that are in those nice pellets. There are others that are basically plastic flakes, and you don't know what is in there. And so having that confidence that you can consistently produce and place these mixtures is very important for the industry. We discussed earlier the method of incorporation, dry versus wet, the different challenges. How do I QC it? Is it a modifier versus a replacement? If I'm doing it wet, how does it really impact my binder characterization? Or can I still characterize these using the same methods that I've been using for my typical polymer modified mixtures? For mixture characterization, how does it impact long-term performance? You know, we have some concerns from a plant operations standpoint of how do we really control this? And if I'm using the dry process and it's those very small flakes or pellets, what happens if some of those light particles get pulled into the bag house and they gum up the bag house? Are there going to be issues with my plant that way? From a construction standpoint, how does it impact the temperature sensitivity and how fast I need to get on these mixtures to ensure I get the density I need for my customers? We mentioned some of the health and safety concerns, the environmental concerns, and it's definitely field performance. We sat down before COVID with our task force for a day and asked questions and tried to figure out what we really needed to know and where those gaps are. And we came up with 4 pages of questions that still need to be answered. But there are high priority ones that we need to understand now that could be game changers or deal breakers if the answers go the wrong way, or we need to then start finding solutions to those questions. So moving forward, the 3 things that I'm encouraging everyone is it's going to take patience, it's going to take partnership, and it's going to take communication. This is not something that we're going to solve overnight. As I mentioned earlier, it's taken us over 40 years to get to actually close to 60 years now, to get to the point where we can put 22% wrap in a mix and feel fairly confident. It's going to continue to take that effort to move forward, and it's going to take research, and research takes time. The challenge that we're facing right now is when I joined NAPA, moving from an academic position, I was told something very early, and it's taken me 3 or 4 years to accept it, but it's marketing trumps engineering every day of the week in general for the public. We could put up all these graphs, but they're putting out a compelling message that we're trying to save the world, the ocean and the world, and your roads are a solution. The challenge is there's not enough data to know if it is really a solution yet. So it's going to take patience. It's going to take partnership. And that's one of the reasons I was actually really excited to be able to come and speak to y'all today, is it's not just us talking within our own countries, within our circles that we're really familiar with. This is a worldwide problem and a worldwide challenge that we're tackling. And so we need to be talking with people on a regular basis to understand, well, what are you doing and how does that reflect with what I'm doing and what can we learn from each other? So that takes communication. It takes us being really open about our successes, and something that we don't like to do is be really open about our failures. There are a lot of times those failures are where we can learn the most. And the challenge with that is you're not going to get picked up in a peer-reviewed journal for a massive failure. So we've got to find new ways to communicate. We've got to find new ways of getting this information. And going back to the partnership, we have to think about some atypical partnerships, or partnerships we don't typically work with. We're going to have to work with people who understand plastics a lot more than I do. As someone who did schooling in civil engineering, I never had to take a class on plastic design or plastic chemistry. It's going to take us talking with chemists. It's going to take us talking with policymakers. It's going to take us talking with people who understand the recycling to really help understand where we can go. So one thing that NAPA did to kind of help try to set the stage is we recently developed 2 reports, a state of the knowledge, which really is kind of what I've summarized today in this presentation, and then a lit review that goes through those 110 plus articles and summarizes them article by article, what we know, what we don't know, and what were the gaps. These are our contribution to trying to help set the stage to understand where do we go next. Because that is what we're doing in the U.S. National Cooperative Highway Research Program has set out, and they have an RFP out, or they had an RFP out to look into the dry process. The Federal Highway Administration just began a project looking at the wet process and binder and asphalt compatibility. If the current appropriations bill that's in the Congress right now is putting another study out there for the national academies to look at the use of recycled plastics in asphalt. So it's very important. It's a very timely topic, and it's something that we're all going to have to do together. So with that, I thank you very much for allowing me to be here and be a part of this today. And I hope that you were able to get something out of this. Those 2 reports are on our website, asphaltpavement.org, and you can get them for free if you just go to the online store. Those are available for anybody and everybody. So with that, I thank you very much.
Hi, Richard. Thank you very much for your presentation. It was a very, very enlightening presentation. I'm very glad to see that how also here in Brazil, we are on the way to begin to pave a very fruitful path as well. And very important words that you said about patience, partnership, and communication. So thank you very much again. And I have here some questions from the audience. I'll begin here with the first question from Camilo Vasconcelos, USP. Thank you, Richard. In my opinion, in your opinion, which type of plastic would be the most promising in terms of performance to add in the asphalt mixture?
I think if you're going to go after kind of the low-hanging fruit, I think polyethylene puts probably fewer hurdles in front of us than some of the others do. So I think that's also reflected in most of the research has focused on polyethylene. Now, it may not be the biggest source of plastic out there, but I think that that's the one that, at least in the U.S., most of our research is really focusing on that at the current time.
Okay, thank you. Another question from Adalberto Vachina, USP São Carlos. A nice presentation, Richard. Do you have results on fatigue, cracking, resistance of asphalt mixtures prepared with recycled plastics? And what about moisture-induced damage of these mixtures?
Yeah, so there really hasn't been a lot of fatigue performance, and I'll be honest, you read a lot of the research, and it's people testing things that you're going to kind of expect good performance in. Like, yeah, it's going to be great for rutting. So let's test it with that. The things that we're more concerned about, that's where you're really seeing the data gap. And even some of the things that have been used as from some of the companies, they've shared some of the data with me that hasn't been really published related to cracking and moisture damage. They still haven't long-term aged those mixes, which I think is really going to impact the chemistry of that plastic as it's exposed to UV rays. I lived in the South US for 14 years, and if I left a piece of a plastic chair in my backyard for 3 summers, I'd come out and I'd try to sit down and I would go through it. And that's for summer. And so I think that long-term performance is really the key to understanding, are we going to get there? And so that's what we've really been pushing people to try to look into.
Great. Another question from here is, are there initiatives or discussions in the USA on the development of environmental regulations regarding the use of recycled plastics in pavements?
So we haven't really started looking at environmental regulations at this point. It's been something that we're going to start having some discussions on, but we haven't started talking to like the EPA or OSHA regarding that yet. One of the things that we realize is when you look at the number of questions and the number of organizations, it's going to take a lot of effort and a lot of money to do all this research. And so we've been trying to get, okay, now that we've got AASHTO committed to doing this research, the next step is then to go to the EPA to see, hey, as we're doing some of these demos, can you pay for some stack testing? Because one of the concerns that we have is, if I'm putting these into the mixtures, especially on the dry process, is that going to change the emissions that are coming out of my plant? I mean, it could be different if I've got a parallel flow plant and those plastics may be exposed to the flame of that plant at an early entry point versus a counterflow or a double barrel type of plant. And so understanding all of those implications is important, and that's something we're going to hope the EPA can help us look into. If anyone from the EPA is listening, we're coming in the near future to talk to you about that.
So jumping and connecting with your answer, I have one question for you specifically about funding. So you mentioned already some organizations and agencies. Would please be more clear who is funding and how usually is the process of funding research regarding the use of plastics on asphalts? So if you can share just who it is and what is the current model that you're using in the USA.
So there are a few major sources of research out there. And so I described the Federal Highway Administration has a project that they are looking into the compatibility of asphalt binder and recycled plastic. So really that wet process. So SPRA has a research budget every year given to them, and they can kind of choose. Well, sometimes Congress tells them what to study. Sometimes they look at it and say, this is really important topic, and so they allocate their research dollars to that. And so that's one of the topics that they recently chose to do. We also have the National Cooperative Highway Research Program, which this is for lack of a better word, a pooled fund where all 50 states contribute money, research dollars to this every year so that they can look at kind of national topics. Okay. And so we wrote a research problem statement and got it to a TRB committee. That TRB committee put it in front of AASHTO. AASHTO said, yeah, we like this. This could be done. We're going to cut the budget in half, but we still like it. And so, but they eventually decided to fund that work. There are other times when Congress writes up how much money Federal Highway is going to have kind of every year to spend. Sometimes Congress tells, through that appropriations process, you're going to look into this and we're going to kind of earmark this money for a certain study. And that's one of the things that's happening right now. In the current draft of the 2021 appropriations bill, there's an $800,000 study that is directed for the national academies to work with the US DOT to evaluate this and look into it more. And so there are different ways sometimes these research projects are funded.
Okay, so thank you very much, Richard. We have in here some more questions that I will address to you, and then you can answer per mail. So again, thank you very much. It's a pleasure having you here with us. So even if virtually, hopefully next time in person in Brazil when COVID let us.
That would be great.
Thank you very much again. Bem, pessoal, agora estamos encerrando esse nosso primeiro bloco de apresentações do dia, está bem? Aguardem, por favor, que a gente vai começar a fazer a transição e em alguns poucos minutos estaremos retornando. Muito obrigado e até mais.